Welcome. Last time got the derivative of exponential functions. Now we are going to use that to differentiate more complicated expressions involving exponentials. The process should now be familiar. Start with the outermost operation, apply the rule for that operation, deal with individual parts in the next step, so on. Let's differentiate x cubed 3 power x. It's a product of two functions, x power 3 and 3 power x. So I have to use the product rule. Product rule says to differentiate each factor at a time, leaving the other factor as it is, and then add the terms that we get that way. In this expression, x cubed times 3 power x, the first factor is x cubed, its derivative is 3x squared. I multiply by the second factor as it is, plus the first factor x cubed times derivative of 3 power x. Derivative of 3 power x is an exponential function, so I have the exponential. But since the base is not e, I must multiply by ln of the base. Since the exponent is just x, we are done. The next example is essentially the same, except that we have some additional things we need to do. Namely, find where the tangent is horizontal. Of course, slope of the tangent is the derivative, and the straight line is horizontal if the slope is 0. So they are just asking in a roundabout way, find where the derivative of x squared e power x is 0. So we will find the derivative of x squared e power x. It's just like the last example. I have a product, so I use the product rule. First factor is x squared, derivative is 2x, times second factor e power x, plus x squared times derivative of e power x, which is just e power x. Since the base is e and the exponent is just x, I don't need any extra factors there. Now I have to set this equal to 0 and solve. And the general technique that works is factoring. So we'll try to factor this. So I'm going to look for factors common to both terms. E power x is a common factor, and so is x. So I'm going to factor out an x and e power x. In the first term, that leaves just 2. In the second term, I'm factoring x out of x squared, that leaves an x. So the factorization is x times 2 plus x times e power x. If this is 0, then one of the factors must be 0. Well, since they said find the points, I have to find the y coordinate as well. If x is 0, I plug in 0 for x, find y. Same thing with 2 plus x. If 2 plus x is 0, then x is negative 2. E power x can never be 0. Exponentials with positive bases are always positive. So we really have just 2 points, x equals 0 and x equals negative 2. But of course I have to find the actual point, including the y coordinate. If x is 0, then y is 0 squared times e power 0, that's 0. If x is negative 2, then y is negative 2 quantity squared times e power negative 2, or 4 e power negative 2. So the points are 0, 0, and negative 2, 4 e power negative 2. Let's do a couple of more differentiations. The next example, I have e to the power x squared plus 1 times square root of x power 4 plus 1. This is a product, so I have to use the product rule. In the second factor, I'm going to write the square root as power 1/2 so that I can use the power rule. So I have e power x squared plus 1 times the quantity x power 4 plus 1 to the power 1/2. Since it's a product, I start by using the product rule. The first factor is e power x squared plus 1. So it's an exponential function since the base is a constant. Take the exponential times derivative of the exponent. And since the base is e, those are the only two things. So the exponential e power x squared plus 1 times 2x, derivative of the exponent x squared plus 1. And then the second factor plus the first factor times derivative of the second factor, x power 4 plus 1 to the power 1/2. Now the exponent is a constant, so I start with the power rule. 1/2 times whatever is inside the parenthesis to the power 1/2 minus 1. 1/2 minus 1 is negative 1/2. Now I must multiply it by derivative of what's inside the parenthesis. What's inside the parenthesis is x power 4 plus 1. Its derivative is 4x cubed. Of course, we can simplify things a little bit and write it in more conventional order. But I'm going to leave the answer in that form. Last example is sort of relevant to some of the other calculations. So it turns out this answer simplified has some significance which won't really directly concern us. So we'll simply treat the problem as a differentiate and simplify problem. This time I have a fraction, so I have to use the quotient rule. So the quotient rule says to differentiate a fraction, take derivative of the numerator times denominator minus numerator times derivative of the denominator over square of the original function's denominator. The numerator is e power t minus e power negative t. I differentiate term by term. First term is e power t, its derivative is e power t. The second term I have e power negative t. Again, it's an exponential function, so I get the exponential times derivative of the exponent. The exponent is negative t, its derivative is negative 1. Times the denominator e power t plus e power negative t minus e power t minus e power negative t times derivative of the denominator. This looks just like the numerator except I have plus sign instead of the negative sign. Derivative of the first term e power t is e power t, second term is plus e power negative t. Its derivative is e power negative t times derivative of the exponent, which is negative 1. We put the whole thing over square of the original function's denominator. Now I need to simplify this. Here I can combine the two minuses to make it a plus, and then I have to FOIL each thing. So when I FOIL, I can use rules of exponents to do the multiplication. E power t times e power t is e to the power t plus t, or e power 2t. And we have to do this for each of the other combination. And don't forget this minus applies to this entire product. So I need to distribute it. I will break it up into two steps. I will just FOIL. And since the bases are all e, when I multiply exponential, I just add the exponents. And we'll distribute this minus as well in the next step. Now I can combine the like terms in the exponents. T plus t is 2t. T minus t is 0. And e power 0 is 1. So I can simplify these terms quite a bit. First term is e power t plus t, e power 2t. And then e power 0 or 1. And then again 1, so on. Now I'm going to distribute the minus in the second group. Now there are a lot of like terms. I have e power 2t and negative e power 2t, that's 0. Then I have e power negative 2t, e power negative 2t, that's also 0. Then I have 1 plus 1 plus 1 plus 1, that's 4. So altogether I have 4 over the quantity e to the t plus e to the negative t squared. This concludes our look at differentiating exponential expressions.